Hi, I'm Chris Kinich, and this is CS361, Systems Programming. Today, we're going to be talking all about threading, how it works, how we're going to use it, and how it goes wrong. First, let's do a little bit of a refresher on what we know already about processes and bring that into what we know about threads and what's different about them. So with processes, we know that an individual process has its memory image, it has its open files, it has its thread of control. So every single process is going to have its code, its data, its heap, and its stack. So in one individual process, we're going to have these different regions of virtual memory that are all in use at any one given point in time. Now, what we realize with threads is we say, when we're scheduling things on a computer, what we're really doing is we're using a CPU to follow a thread of control. Like we're going to step through a bunch of different stack frames. We're going to execute a bunch of text. It would be nice if we could reuse all of this, but without having to duplicate it into a whole nother process, right? We know with fork and POSIX spawn, yes, we can fully duplicate this and then have two different threads of control, but they all exist within their own universe. If we want to operate on a bunch of data that's shared between the different workers that are working on that data, but we still want to take advantage of multiple CPUs that could potentially run these threads of execution in parallel. What we can do is we can say, well, we don't need this whole entire big new process. What we really need is more than one stack. So what we can do with threading is we can create other stacks. So this is stack sub 2, this is stack sub 1, stack sub 3, and every single one of these stacks is going to live within the same exact memory layout, but they're each going to have a stack pointer that points to someplace slightly different based on what they're doing. They're each going to have their own copies of local variables, unless they're static, but everything that's in the heap is visible to everybody. Everything that's in the globals is visible to everybody. The nice thing about the heap is that while it's hypothetically visible to everybody, if I'm in one worker thread and I call malloc, as long as all the other threads are working correctly, that memory is mine and mine alone. Malloc is thread safe. It will allow me to have access to some arbitrary amount of memory that I ask for without having to worry about what the other threads are doing at that moment in time. So this is all fine in theory. Kind of this makes sense. Yes, like I feel like I'm following along. You probably feel like you're following along. But I would imagine it'll be a lot more useful for us to go and look at how this code would actually run in an actual real live living example. So what we have here is our real live living example of how to use threads in the most basic way possible. What we have here is a super basic program where we're going to launch two different threads, one which will withdraw a certain amount of money from an account. The account balance is stored as a global variable, so all threads have access to it. There is a thread which gets created that will deposit cash into that account, and it's also going to deposit $10. And then our main thread is going to wait for those two threads by calling join, and then print out the final balance before exiting the entire program. Each of these individual worker threads is going to be started here with this either deposit or withdraw. These are void stars, which return void stars. However, we still can pass in arguments to these functions. What we have here is I know that this function only takes one argument, and so I can just pass in a pointer to that argument. So here I have an amount that I'm going to call this with, and I'm going to add that to the balance when I deposit cash. Kind of makes sense. And something that you'll also see a lot very often is, say, if you're accessing something from a database, you're going to request that balance, you're going to perform some computation on it, and then once you finish that computation, you're going to store the result back to the database. You're going to update the database with that new piece of information. Likewise, withdraw is completely symmetrical with deposit, and these get and set functions are also up here. Now here, we're going to simulate something that takes a little bit of time in each of these individual threads. So we're simulating a blocking call to a database here, where we sleep for a quarter of a second and then we return the balance. Likewise, when we set the balance, we sleep for a quarter of a second, then we return. This makes sense. This is a reasonable simulation of how things would work in the real world. So let's see what happens when we run this code. I've got this repository set up such that both the build command and the debug command are set up to work correctly. So if I were to say do something like Control-Shift-B, that will build this program, and I'll see whatever errors GCC had given to me. So if I put something in here that's obviously a syntax error, I hit Control-Shift-B again, I'm going to get these nice little squigglies that tell me that a problem has happened. And B, I'll also see a list of all of the errors that GCC found with my code. So that works nice and quick. I can go in there and fix that however it is I need to fix that, save it, Control-Shift-B it again, and no problems. No more squigglies, no more errors, no more warnings as we see down here, because we're all built and we're good to go. The other cool thing here is that not only will we be able to just build it with a Control-Shift-B, we can also run it, and if it needs to be built, it will be built by hitting F5. What F5 is going to do is it's going to start GDB within VS Code, running this specific program, whichever one I have open in the current window, and it's going to pause on entry to the main function. So now we can watch as we step through this code. I would highly recommend stepping through and experimenting a little bit with how these things work, because it will give you a much better idea of how threading actually works. So I'm going to keep hitting F10 over and over and over again. That's just going to step over the code that I'm currently on and move on to whatever the next assembly instruction ends up being. Here, we are going to call printf. I can step into printf by hitting F11, and we can see here that our GCC was really smart. It noticed, oh, you don't need printf, you just need puts, and it compiled down to calling puts. The way that this container is set up, you actually have access to the source code of everything in glibc. So anything that's in glibc, if you want to actually see how it works, you can just step into it. Whereas usually you'd have to do a bunch of configuration to get that to work correctly. So we can step through and see exactly how IO puts is going to put that information out to the screen. And we see that it actually did go through that whole entire thing. But another option that we have is if I hit F11 to jump into something. So I'm like, you know what? I actually don't care how this works. I care how my program works that I just called from. I can hit Shift F11 and that will pop back out to wherever it was I was before this. So now I have finished calling pthread create at this moment in time. And the really interesting thing here is that I can see my call stack of that call to withdraw cache. So withdraw cache is currently waiting in get balance. So get balance is actually waiting. It's doing a system call to wait a certain amount of time, but it's paused. Obviously, more than 1/4 of a second has passed since I looked at this code. It isn't moving. So an interesting thing to know here is that if you step through via a debugger, it's going to by default pause all of the other threads, which is really, really useful when you're trying to figure out what's going on with your multi-threaded program. Now, if I were to hit F10 here, that would actually continue the get balance function. What I want to do instead is go back to my main thread and hit continue here. Remember, we're in get balance right down there at this moment. If we move forward, we are now looking at the create result. We're waiting for the create result test to say, was it 0 or non-zero? Did this function create a thread successfully or not? But if we switch back down to threading, we're no longer where we were before. We were previously on line 74 waiting in the get balance, but now we're waiting in the set balance. The really important part about this is that whenever we step, what we're fundamentally doing is telling the operating system, I want you to set up a trap on a specific instruction, say the JNE of this create result bang equals 0. When you get to executing that instruction, trap to GDB and allow GDB to inspect what's going on. That's how you use the debugger. But the interesting thing there is that all of this is asynchronous. When I tell my code to continue on until the next step, what I'm really doing is saying, go do whatever it is you want to do until this main thread gets to this specific assembly instruction. In the time between when I was on the previous line and when I'm on this line, anything else can happen that can work in the rest of the threads of this program. And that's exactly what happened here. We were previously on the get balance line, but our wait certainly finished and we got unblocked and we printed our things to the screen that we wanted to print. Then we went down into set balance, but we got to the next line within 250 milliseconds, and now we're waiting here in set balance in this worker thread. So if I were to hit F10 again here, I'm going to move on, presumably, if create result is itself 0, which it is, we can see that. That's going to move on to that line 44 probably. So now that I'm on line 44, all of a sudden, I am not seeing any other threads. That other thread is completely finished because it got to the end of its withdraw cache function. It got to the end, it returned null, it was done. It printed its new balance, all that is good. Everything is fine with the universe. So we still have one thread here. And what happens here isn't really going to be surprising. We start that new thread, we can pop it open, see where it is. We can continue stepping in main. We see that during that step, the worker thread moved from being on the get balance to being on the sit balance line. And our join is going to wait for that first thread. That first thread is obviously terminated, so it's going to immediately move on to the next one. The second thread, as we can see here, is terminated. We move on to the next one, and we see that my balance is now $100. Because if we were to set up, say, a watch here, we could set this to my balance, and we'll always see that our balance is a certain amount. So I can hit F10 here, I can hit F10 here. This is actually going to go into the libc start. So we can keep going until we actually hit the exit call, which is coming out of the thing that called main, and we're done. We've gotten through, and if we do this again, we just hit F5 here. We can step through. Our watch is still there. We can see all of our local variables. We can jump into the different functions. We can watch as everything happens bit by bit. We can see that our balance went down. We see that our balance goes back up, and we print out our balance. So I could run this over and over and over again. And as long as I'm going through, kind of slow the way that I am, there aren't going to be any problems whatsoever. The tricky part is that that's not always going to be the case. So for instance, rather than waiting for every one of these lines to run, I instead just run it at the command line. I will see something very different happening here. So I'm going to run threading. I wait a little bit of time. My balance is 110 after depositing 10 and withdrawing 10. I probably should be back at 100. Let's see if I run it again. Okay, 110. You see that again. Up, 110. Up, 90. Okay, so the way that this is written, it probably will never work correctly just because of the way that the timing works. So you can imagine that this is a tricky thing for us to A, recognize is actually a problem, because sometimes it's not going to happen every single time like it is here. And B, we've actually got to figure out how to prevent this from happening. So I don't know whether this is a useful thing for everybody, but I feel like using this game called Factorio is a really good way to really visually see what's going on with threads and where things are going to go wrong. This is a good analogy, so just stick with me. So really quickly, Factorio, one of my favorite games. It's a really fun kind of logistics simulator, but it also has some adventure aspects to it. The nice thing here is that it has a really great train simulation that is a very, very good way for us to better understand how semaphores and mutexes and stuff like that work. So what I have here is 2 train tracks, and these 2 trains are just going to go around and around and around forever. So I can take this one, tell it to start going back and forth between these 2 different places. That's just going to go around and around and around and around forever. And I can take this other train here, and I can also tell it to go around and around and around forever. So the interesting thing that we're going to see here is that they're doing something very, very dangerous there. Oh, and they're already stopping, hitting each other. Okay, let's pause this for a second. You pause, you pause. So obviously something bad happened there. We've got 2 trains, they ran into each other. That's not good. The way that we can solve that problem in this game specifically is put in some train track protection. So let's do that. So we got these rail signals. So let's start this over again. Let's try this one more time. What I can do in this game specifically is I can set up some train signals that will prevent the train from entering an area unless no one else is in that area at the same time. So what I've just set up here is a set of mutual exclusion locks, which will prevent any sort of run-ins between these 2 trains. What I see here is whenever I see a green here, that means that this lock is unlocked. And that lock handles everything that's within that purple region. So if somebody's in that purple region, that lock is going to turn to red. This one's going to turn to red, because what Factorio is providing for us as an invariant is that any one individual colored segment can only have 1 train in it at any one given point in time. And I can create these different segments by splitting them off using these train signals. What these train signals will do is purely create another segment. So here now I have this blue segment and this yellow segment. I can get rid of that one, and so now I only have that one blue segment. So now, if I start my trains again, they are going to be safe. Only one of them will enter that area at any given moment in time. So this is pretty useful for us, right? So even though they're doing exactly the same thing that they were doing before, and it almost looks identical, they are actually going to be slowing down and making sure that only one of them is in that mutual exclusion block at any one moment in time. What I like about this analogy is that what we have here is something that's correct, but it's not necessarily as efficient as it could possibly be. So I've stopped these two trains, and now we're going to do a little experiment here. So what I just drew there is very, very coarse-grained. What this is coarse-grained locking, where I say this entire region is all mutually exclusive. Only one train is allowed within this region at any moment in time. But you can imagine, especially if we think about how train tracks work in the real world, I could say, oh, well, usually we just have crossing guards like this, where we say only one of these trains is allowed into this specific region at any one given point in time. And likewise, this other intersection down here would have the same situation, where it's going to say, okay, when you're going into the intersection, that's when you want to be careful and make sure that only one train is in there at any one given point in time. So that's finer grained. What's useful about that is if we start our trains up again, they're still going to run correctly, but they're going to be a little bit more efficient. You probably won't be able to see it in this specific example, but we do have a world where one of them could enter that intersection and be halfway through, and then the other one could enter. So for example, one of our trains could be right down here while the other one is approaching. And then that other one, because the first one has cleared this intersection, it would actually be allowed to enter the intersection. What we're going to see in the next week's lectures is that this is a good idea. This definitely makes our trains more efficient. This makes our locking more efficient by being more fine-grained, but we do run the danger of creating deadlock. So now that we saw how to solve this in video game world, let's see about how we're going to solve this in programming world. First off, we're going to want to create a mutex. So the book covers semaphores, which are a very good foundational way to think about this at a very historical level. I'm going to focus primarily on using mutexes here instead of semaphores. A mutex is a special purpose version of a semaphore that only counts from 1 down to 0 and back up to 1. At the end of the day, semaphores and mutexes function very, very similarly, but a semaphore allows more than one thread to gain access to a lock before actually locking everybody else out. At the end of the day, semaphores aren't a super useful primitive for doing the types of synchronization that we typically do in programming. So I'm not going to use it too much for these implementations, but it will be important to remember how semaphores work, especially for any sort of systems programming interviews that you may do. Anyhow, let's get this started. The first thing that we're going to want is a pthread mutex t lock here. So I'm making this as a global so that all of the threads will have access to it without having to have it passed to them manually as a reference. And in the beginning of main, I am also going to initialize that. So pthread mutex init, and I'm going to pass in a reference to that lock. And I am going to not care about the mutex attributes. And now I have to decide how to do the locking. Now, the first thing that we could do that wouldn't be very correct, but would lead to correct operation for our program is to simply start the lock here and only unlock after we have finished this entire program. So if I were to say pthread mutex lock of lock here, and then I wait for that thread to finish, and then I do a pthread mutex unlock, and honestly, I probably don't need to do it here, but just for the sake of symmetry, we do our pthread mutex lock and unlock up here. So we do this, we do this, we format, we save it, and we run it. So we build. So I'm going to run it. Yeah, so every single time I run it now, I'm not getting a super strong guarantee, but I'm seeing, okay, what I expect to happen, I'm always seeing a balance of 100, is happening here. But what we just did was we completely removed any sort of concurrency from our program. We said run one thread until it's finished, stop, and then run the other thread until it's finished, stop. And you can see here it takes about a half a second each time I run this to actually get through. So we're seeing, we can use mutexes, but sometimes if we put them in the wrong place, we're going to make our code no longer run parallel. We're going to get rid of all of the benefit that we got out of doing the hard work of making our code multi-threaded in the first place. What we can instead do, say, you know what, let's use that railroad analogy. Let's only protect the areas of our code that are dangerous. So I'm going to put this pthread join back down here. I'm going to get rid of these locks and unlocks. And I'm going to say, okay, what's dangerous here is I get this balance, I modify it, and then I set it. That's the dangerous thing here, because this takes a certain amount of time, and then I have a version that may not agree with the version that is set in the global variable when I overwrite it with this new value. So what I might want to do here is a pthread mutex lock on lock and a pthread mutex unlock right here. And I can run this and it's going to do absolutely nothing. It's going to work basically the same way that the previous version did. And it's not going to protect everything. So just because we protected one access to this doesn't mean we're going to be home free. Even though this specific part is protected, if only one thread is using the mutex, then it's not really going to do anything in the first place. This would be like the train example, but only having one of those trains actually paying attention to those green lights, red lights. What we need to do instead is do this same protection down here in the other thread as well. So now that we've built, we can run it, and we run it over and over and over again. We see that we're running both of these threads at the same time. They're both doing what it is they need to do, but we're still kind of going a little bit slow. So as we see, we're still kind of a little bit slow here, right? It's still taking about a half a second every single time we run this program, and it's good because it's now currently correct, but we didn't actually receive the benefits of multi-threading here. So one important thing here is that if there was a whole bunch of other computation that happened outside of these critical sections, that's our vocab word for these areas where we could be leaving the memory in an inconsistent state, we would be able to get the benefits of concurrency outside of that mutex lock, but everything that happens within it is only going to happen on one processor at one point in time. It's mutually exclusive access to that code. So this entire region and this entire region will only run one at a time. And we need to do that because this is dangerous. We're getting something, we're modifying it, we're setting it back. That's going to be very similar to the way that we're doing it pretty often in lots of different places. And just like with the train example, what's going to end up happening is this pthread mutex lock looks to everybody like a green light until they come to it. As soon as one of them comes to it, that green light will turn red for everybody else, so that they have to wait until that person has exited their critical section, then the light will turn green, and the operating system is only going to allow one thread into that critical section at any one moment in time, just like our train signals in Factorio. So I'm not going to commit the changes that I've made here. You can see all the green gutter marks showing the text that I've changed in here. However, what I do have in this repository is a threading example that's broken, a threading example that's fixed that does the same thing that I have here, probably with slight differences in naming or in exactly what line was being used. So what we have here is threading.fixed is everything working correctly with mutexes, and threading is the version that has no mutexes and causes incorrect operation. Thanks so much for watching, and I'll see you next time.